All right, in today's lecture, we're going to take a look at precipitation reactions and the process of precipitation. And that's going to segue us into a much broader topics. Well, without further ado, let's get things started. Let's get things started by taking a look at the precipitation reaction of lead 2 nitrate with potassium iodide. All right. Here's one of my favorite classic examples of a precipitation reaction. I have potassium iodide and I have lead 2 nitrate. And if we look in, we can see that they're both liquids, right? No solids. Matter of fact, my lead 2 nitrate is rather clear. My potassium nitrate is also very clear. Kind of a yellowish tinge, but it's clear. You can see there's no particulate matter in it. We're going to perform a precipitation reaction where we take two salts that have been dissolved in water and are soluble in water. However, when we mix the two salts, we wind up forming a solid, and this solid is going to fall out of solution. We call things that fall out of the sky, such as rain or snow, precipitation. We call things that fall out of a solution a precipitate. So we're going to form a precipitate. Got my potassium iodide here, going to pour it into my lead 2 nitrate. Dramatic action shot. Zoom in. Whoa! Whoa, look at that. Look at that. And what you'll see here is I now have not just a color change, but if you look at the sides of my beakers there, you'll see that I have little particles. Specifically little particles of lead 2 iodide. That lead 2 iodide that's now come out of my solution is a precipitate. And what you're going to learn in today's lecture and in today's lab is how to predict when a precipitate is going to form. Oh, look at that. Look at that. Look at all that lead 2 nitrate there. All right. Chemistry's easy, life is hard. All right. So now you've actually seen a precipitation reaction. Specifically, what is it that we were looking at? We saw in that demonstration that we took lead 2 nitrate, aqueous, we reacted it with potassium iodide, aqueous, and we produced lead 2 iodide, solid, and potassium nitrate, aqueous. We saw that a solid came out of the solution. That yellow, those little yellow granules were your lead 2 iodide, and it's referred to as your precipitate. Just like we have things falling from the sky, and we call stuff that falls from the sky precipitation, we call things that fall from a solution a precipitate. Solid that comes out of a solution is referred to as a precipitate. Now, the great thing about precipitation reactions is that they're really love stories. If we look at what it really occurs during a precipitation reaction, we can see what we're talking about. Remember, we talked about electrolytes, and we said that anytime you have an ionic compound dissolved in water, it's like the ionic compound got a divorce. We have lead 2 nitrate here, and it's aqueous. That means that if we looked inside our beaker that contained our lead 2 nitrate, we wouldn't find lead 2 nitrate as a unit, right? We would actually find a solution of water that contained a bunch of lead ions floating around and a bunch of nitrate ions floating around. Why? Because they decided that they were more attracted to water molecules than they were to each other. Right? It was nice while it lasted. They dated for a while, But man, those water molecules came through with those nice positive and partial negative charges, so they split up. Same for potassium iodide. Splitsville. They got together too young. They realized how much they'd grown apart when the water molecules came along. So if we looked inside our beakers before we carried forward the reaction, we'd see a bunch of lead 2 ions floating around and a bunch of nitrate floating around. And in our other beaker, right, this is one beaker. And in our other beaker, we'd have our potassium ions and our iodine ions floating around, right? When they're dissolved in water, your ionic compounds have split up into ions. Well, when we mix them together and put them in one beaker, what have we done? We've doubled the dating pool, right? Previously, our lead had been stuck in a dating pool where the only things to date were nitrate ions, which it didn't get along with, or water molecules, which were nice, but it's really looking for an ion. Well, when we mix these two solutions together, suddenly there's a new ion with a negative charge for our lead 2 date. The iodide ion, right? So those two are going to go out on a date. And what happens? Happy, happy, joy, joy. It's true love. Turns out that our lead and our iodide are so attracted to each other that they decide to get married. And they leave the dating scene, right? They literally fall out of the dating scene. They literally precipitate out of the dating scene. These guys have found true love. They are more attracted to each other, our lead and our iodine are more attracted to each other than they are to the water molecule. Well, you know how it goes. The X's are hooked up, so we're going to try to make them jealous by hooking up as well, just because it seems the thing to do. Not only that, but we're going to have to be there sometimes together on holidays and weekends. So the potassium and nitrate try dating. However, they don't really have any attraction for each other. They'd rather dance around with the water molecules than get married. So even though the potassium and the nitrate date, and they're in the same dating pool, it looks like they're together because we list them together, but how do they exist really? Well, they're aqueous, so they're not finding true love. They're really still out there floating around in the water. So if I'm to do a little cleanup here, what we could actually say occurred in this reaction is we could say from an ionic perspective that we had lead and nitrate breaking up. We had potassium and iodide breaking up. They all four find themselves at the same club. Awkward. However, it has a happy ending because our lead and our iodide find each other, get married, leave the dating scene. They fall out of solution to form a precipitate. Not so happy an ending for our potassium and our nitrate, however. Even they go on, though they may go on a few dates, they don't find true love, and they wind up going back and floating around that great discotheque of water. When we write chemical reactions, we write chemical reactions like this, right? That's how we're used to viewing chemical reactions. And how we're used to viewing chemical reactions is referred to as a molecular equation. What I just wrote for you down here in this big circle, this is how things physically exist, right? This is how our compounds and our ions are physically existing, right? Our soluble compounds physically exist as separated ions. Our precipitate physically exists as a solid of lead and iodide desperately clinging to each other in the great romance of a precipitate. This equation that shows how things physically are is referred to as a ionic equation. If you look at this ionic equation, our love story's cluttered by talking about the X's, right? Potassium appears on this side of the equation and this side of the equation unchanged. Same for our nitrate. Potassium and nitrate aren't finding true love, so why clutter up our story by talking about the X's, right? Who starts off a great romance by talking about their X's? Oh wait, Ted Mosby does. Matter of fact, Ted Mosby goes on and talks about, I believe they said it was 27 different X's before he talks about his current wife. But anyhow, I digress. Great show. If you've never watched it, Netflix it. But as chemists, we often want to clear the scene. And we clear the scene by representing what's physically occurring by crossing out those things that aren't part of the story. In our ionic equation here, potassium is the same on both sides of the equation. So is our nitrate. So if we were interested in telling the core story of the reaction, we're really focusing on just the two ions that fell in love, our iodide and our lead. We would say that this is the reaction that actually took place. We would refer to this view as our net ionic equation. Before the end of the next couple lectures, I'm going to be able to give you two reactants, and you're going to be able to tell me what the products are. You're going to be able to tell me the phase that those products are in. You're going to be able to write ionic equations and net ionic equations. Don't worry, though. This is just a preview. We're going to break it down one step at a time, hammer style. All right, let's get started. In terms of breaking it down, there's a lot of little sub-goals that we need to achieve. The first of these sub-goals is to predict if an ionic compound is soluble. And that may or may not be throwing out a new term for you. Soluble means dissolves in water. And how do we denote something in terms of phases when it's capable of being dissolved in water? When something is capable of being dissolved in water, we write an AQ next to it for aqueous phase. The opposite of being soluble is insoluble. For ionic compounds, that means they would be in the solid phase. Note, for covalent compounds, if they're insoluble, they could be liquid, they could be gas, they could be solid, right? But for ionic compounds, if they're insoluble, meaning they can't be dissolved in water, then they're going to exist in that solid phase here. So our first goal is for me to be able to give you an ionic compound, and for you to be able to look at that compound and tell me if it'll dissolve in water or not. Before we take a look at that, though, why don't you write down the word Colts? Write down the words Colts. C-O-L-T-S, Colts. In order to determine whether or not an ionic compound is going to be soluble or not, you have to memorize some solubility rules. Sorry, no other way to avoid it other than to say the dreaded word memorization. However, if you're at one of my at-home gamers, this gives you a slight advantage, right? Because instead of memorizing, you can print out the next 2 slides here on solubility rules for solubility and insolubility. As a matter of fact, if you have not done so already, pause me and print them out, because this is one of those times where having the handout in front of you as I'm lecturing is going to be really, really useful and beneficial to you. I would even argue crucial to you. All right, so these are your solubility rules. If I was to summarize them, and we'll go through them one at a time here in detail, but if I was to summarize them, in other words, I was wanting to avoid a lot of memorization, ionic compounds where you have a cation with a positive 1 charge or an anion with a negative 1 charge, chances are that ionic compound will dissolve in water. That's the quick, dirty way of looking at these 4 rules. Now, you can see just glancing at them, they're more complex than that. So let's go through them one at a time. All right, your first rule, and this is a rule to which there are no known exceptions. If it conflicts with any other rule, this rule's always right. Group 1A elements and ammonia containing compounds are soluble. No exceptions. How would we rule this? How would we use this rule? Well, we would use it like this. Is potassium carbonate soluble or insoluble? Well, we see it contains potassium, and potassium is a group 1A element. So if it contains a group 1A element, it's soluble. So we would know that this would be soluble in water, and that's a cursive AQ. People always question my handwriting. Down here, we have another compound. We have ammonium phosphate. Is it soluble in water? Well, we see it contains ammonium, and anything that contains ammonium is soluble in water. So it too would be soluble in water. See, chemistry's easy, life is hard. Your second rule is equally as easy. Any compound that contains acetate, nitrate, or perchlorate are soluble, meaning they're going to dissolve in water. So if your ionic compound contains one of those 3 ions, they're soluble in water with no exceptions. So we have calcium nitrate. Is it going to be soluble or insoluble? Well, we see it contains nitrate. Since it contains nitrate, it's soluble in water. Down here, we have iron 2 acetate. Is that soluble or insoluble? Well, we see it contains acetate. Remember, acetate can be written more than one way. We see it contains acetate, so it's soluble in water. Chemistry is easy, life is hard. And again, there are no exceptions to this rule. There are exceptions to this rule, however. Most chlorides, bromides, and iodides are soluble, except silver, mercury 1, and lead 2. Except silver, mercury 1, and lead 2. Know these exceptions. These exceptions are important. What do you think I'm going to ask you on exams? Darn right, I'm going to ask you those exceptions. Not just because I'm wanting to make your life miserable and give you something extra to memorize. I'm going to ask them because they have a great deal of use to us in the laboratory when it comes to separating things and performing qualitative analysis. And we'll go into that in more detail later. But right now you need to know that most chlorides, bromides, and iodides are soluble, except silver, mercury 1, and lead 2. So again, let's apply this rule. Is nickel 2 chloride soluble or insoluble? It contains chloride, and nearly anything that contains chloride is soluble. So nickel 2 chloride would be soluble in water. How about lead 2 bromide? Well, most bromides are soluble, but wait! We don't get to do it to dissolve our PBJ, or our PBB. If I ever have an element, I will so name it J. But at any rate, our now I'm totally thinking about lunch. At any rate, it contains lead, right? And lead is an exception. Since it contains lead, and lead is an exception to the solubility rules, that means that this is insoluble, and it would be a solid, or would remain a solid if we placed it in water. So it's insoluble because it's an exception. Our last solubility rule is the one you have to watch out for. It's the one that bucks that trend. Remember I said most things that have positive or negative ones are soluble? Look what we got here. We have sulfates. And to refresh our memory, what's sulfate? SO4, 2 negative. Most sulfates are soluble. The exceptions to this rule can be broken down into 2 categories for memorization. First, round up the usual gang of suspects, right? The same 3 troublemakers that we had for our chlorides, halides, and iodides are also troublemakers for our sulfates. Then we throw in 3 more suspects. Rather than memorize these guys outright, look where they're located on your periodic chart. I know you have a periodic chart in front of you because you wouldn't dream of sitting down for a chemistry lecture without one. But if you look on your periodic chart, group 2A, what do you see? You see calcium, strontium, and barium. What do you do with the dead chemist? Well, first you try to helium, and if you can't do that, you hope you can curium. And if you can't do either of those 2 things, then you gotta barium. Ba-bum-bum! But at any rate, try the salad bar, folks. I'll be here all week. If you look at your periodic chart, they're all right in a row there in group 2A. It's that lower part of group 2A. Calcium, strontium, and barium. So I call them my gang of 2 for memorization purposes. And they'll pop up again as exceptions on other items here later. So let's apply this rule. Most sulfates are soluble. So we look at this compound. It contains sulfate, so it's soluble. It also contains potassium. So anything that contains potassium is also soluble because potassium is a group 1A element. So that was our first rule there. So this has 2 rules that tell us it's soluble. Next, we see calcium sulfate, and we're saying, well, we see sulfate, so it must be soluble. But then that alarm bell goes off. It sounds like a crow caw-cawing at us. Caw-caw, 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 reminding us that calcium is an exception to the sulfate rule. So because it contains calcium, which is an exception, it's going to be insoluble. Here are the insolubility rules. I was getting ahead of myself there, apparently. There are also two rules that tell us when things will be insoluble. Two rules that tell us when things will be insoluble. Compounds that contain phosphates or carbonates are insoluble. Compounds that contain sulfides and hydroxides are insoluble. Note, if we were to do a quick and dirty trend for our insolubility rules, they all have charges with an absolute value 2 or greater. But let's take a look at these rules one at a time. First, compounds containing phosphate or carbonates are insoluble. The exceptions to this rule are simply our first rule, right? Anything that contains a group 1A element or ammonia is soluble. So really this isn't something we need to memorize. You just need to remember that our first rule has no exceptions. So we see magnesium carbonate. Anything that contains carbonates are insoluble. Solid, insoluble, it would not dissolve in water. Down here, we're getting a little bit trickier. We see carbonate, so we're saying, yay, it must be insoluble in water, but then what's our carbonate bonded with? It's bonded with rubidium, and rubidium's in group 1A. And anything that contains a group 1A element is soluble, so this would actually be soluble. Then we come to calcium phosphate. Anything that contains phosphate is insoluble. Is calcium an exception? No, it's not. So calcium phosphate is insoluble. Remember, solid means insoluble. Then last but not least, we have sodium phosphate. Well, even though anything that contains a phosphate is insoluble, it's bonded to sodium. Now remember, anything with a group 1A element is soluble, and that rule always takes precedence. There's no exceptions to it. So because sodium's a group 1A element, our substance will dissolve in water. So it would be soluble. Looking at our next rule, compounds that contain sulfides and hydroxides are insoluble. Now our exceptions expand a little bit. If you look, our exceptions are no longer just the group 1A elements and ammonia, but now include, hey, those three suspects we saw before. Calcium, strontium, and barium, that same old gang of two. However, last time we were seeing things, they made things insoluble. This time they're going to make them soluble. So they're the same exceptions, but they're having the opposite effect. So anything that contains sulfide or hydroxide is going to be insoluble. Let's take a look. We have barium sulfide. We have a sulfide, so that says it's insoluble, except barium's an exception. So that means that it does dissolve in water. We have potassium sulfide. Anything with sulfide should be soluble except group 1A elements. Darn it! So since it has potassium, a group 1A element, it's going to dissolve in water. Then we have iron 2 sulfide. Anything that contains a sulfide is insoluble, so it would not dissolve in water. Then we come over here. We see hydroxide. Anything with hydroxide is insoluble unless it contains calcium. Calcium's an exception, so it will dissolve in water. Sodium hydroxide also will dissolve in water because sodium's a group 1A element. However, if we had magnesium hydroxide, Would it dissolve in water? No, because magnesium is not an exception to the rule. So magnesium hydroxide would not dissolve in water. I know, I gave you lots of examples of the exceptions there. Why don't you write down the Bengals? Write down the Bengals. B-E-N-G-A-L-S. Bengals. I hope everybody's writing down the Bengals. All right. If we were doing this together face to face, I would shut up right now, and I'd have you do this at your seat and walk around your room and look over your shoulders in an attempt to make you nervous. But since you're not doing this face to face with me at the moment, pause the video and try to determine if the following substances would remain a solid or be aqueous if you placed it in water. Pause me. Pause me. Pause me. Pause me. Oh, come on, guys. It's not that hard. Pause me and try it on your own. Did you pause me? Some of you out there didn't pause me. All right, so let's take a look together. First up, we have strontium carbonate. We have a rule that says anything that contains a carbonate is insoluble. However, is strontium an exception to that rule? No, it's not. So carbonate will not dissolve in water. It will be insoluble. Next we have, I'm going to go down here, we have potassium sulfate. We have a group 1A element. Anytime we have a group 1A element, our compound is soluble, regardless of what it's bonded to. So it will dissolve in water. Next up, we have calcium sulfide. Anything that contains a sulfide is insoluble except for calcium. Since it's a calcium sulfide, it's soluble in water. Anything that contains lithium, which is a group 1A element, is soluble. Sodium's a group 1A element, so it's soluble up here. Then we have iron 2 sulfate. Anything that contains sulfate is soluble. Barium hydroxide. Anything that contains hydroxide is insoluble. However, barium's a exception. Hey, what did you do with the sick chemist? Oh, whoops, I already told that one. Then we have silver iodide. Anything that contains anything that contains iodine is soluble except for silver, lead, or mercury. So this actually will not dissolve. It'll remain a solid. Then we have iron 3 iodide. Well, anything that contains iodide will dissolve in water. Then we have copper 1 chloride. Anything that contains chloride will dissolve in water, so it'll be aqueous. Then we have ammonia, and anything that contains ammonia will dissolve in water. So that's it. Chemistry is easy, life is hard. Let's keep moving. How can these precipitation rules prove useful to us? Here's a classic chemistry example of how they can prove useful. And these are the type of questions I love asking on exams. And you'll use quite a bit in the laboratory. You'll be quizzed on this and expect to know this really well for lab. But you have an aqueous mixture of sulfide and sulfate. What could you add to the solution to precipitate the sulfate but not the sulfide? In other words, which of these 4 cations would form a solid with sulfate but not with sulfide? Well, let's see, ammonia. Anything that contains ammonia is soluble. Well, that means it won't form a precipitate or a solid with anything when you add it in an aqueous environment. Same for sodium. Sodium's a group 1A element. So it's not going to form a solid with anything, quite frankly, in the presence of a water environment. Barium. Let's see. Barium is an exception to the sulfide rule, right? Anything that contains sulfide forms a solid except for barium. Barium's one of the few things that sulfide can bond with and allow it to remain aqueous. However, barium's also an exception to the sulfate rule. Most things that contain sulfate are soluble except when they contain barium. So barium sulfide actually wants to be a solid. So if we added barium to a solution of sulfate and sulfide, it wouldn't react with the sulfide at all, but it would react with the sulfate to form a solid. So it would be the answer to our question. What about silver, you're saying? Here's the problem with silver. Silver absolutely would react with sulfide, and anything that contains sulfide is a solid. So yes, silver sulfide would form a solid. However, silver's also one of the solutions to is also one of the exceptions to the sulfate rule. Anything that contains sulfate is soluble except for silver, mercury, lead, and that gang of 2. So if you added silver to your solution, both your sulfide and your sulfate would become solids. Only by adding barium could you allow the sulfate to come out of solution and the sulfide to remain into solution. At home with a quick illustration, I have a solution of barium and sulfate floating around. If I have a solution of sulfide and sulfates. If I add barium, barium only forms a solid with sulfate, right? It doesn't form a solid with sulfide. So if I added barium to my reaction vessel, what I'd get barium and sulfate forming a solution, sinking down to the bottom here. But it wouldn't react with my sulfide, so my sulfide would remain floating free. Chemistry's easy, life is hard, and we'll make use of selective ions like barium in the laboratory to help us separate mixtures of things like sulfide and sulfate. All right, let's kick the reaction up a notch and use these solubility rules to determine the outcome of a reaction. Our goal here in this part of the lecture is for me to give you a reaction and for you to be able to tell me what the product is going to be. In other words, if I tell you you're mixing silver nitrate with potassium chloride, I want you to be able to tell me what goes on the other side of the arrow. Note, it's not enough for you to be able to tell me what compounds are going to be on this side of the arrow. You need to be able to tell me what phase the compounds on the other side of the arrow are going to be in. Fortunately, this can be done in 4 really, really easy steps. All of these steps you've actually met before, so really we're just stringing together some old concepts here. All right, so let's look at our reaction of silver nitrate and potassium chloride. The first thing we want to do is list the ions. Remember when we talked about electrolytes, we said an ionic compound dissolved in water breaks up into ions. So we want to break our ionic compounds up into ions. You do that using your nomenclature rule. The most common mistake I see on these type of problems is people wanting to invent ions. If it's not an ion you've seen when you did your nomenclature, Don't do it here. All right, so we have silver nitrate. So we have the silver ion, and we have the nitrate ion. Then we have potassium chloride, so we have the potassium ion, and we have the chloride ion. So that's step 1. Step 2, make new compounds by pairing the inside ions and the outside ions. Remember, cations always go first. What do I mean by pairing the inside ions with the outside ions? This is kind of like foiling in math class. Remember, ionic compounds have to form by reacting species of the opposite charges. Silver and nitrate have already tried to get together to form a solid, and it didn't work out, right? They enjoy each other's company, but there's just nothing there. Same for potassium and chloride. What's the only other negative charge for potassium to date? Nitrate. What's the only other negative charge for silver to date? The chloride. The pattern that will never fail you, it will always hold, is your new compounds are going to be formed by mating your outside ions and your inside ions. Your outside ions, your inside ions. Use your nomenclature rules to form your compounds. Silver is +1, chloride's +1, so it would be silver chloride. My other compound would be potassium and nitrate. Remember, your positive ion always goes first. Second biggest mistakes I always see. Positive ion goes first, so potassium, nitrate, again a 1-to-1 ratio. So those are my two products. So I come up here to my reaction. I have my two products now. I've got silver chloride and I have potassium nitrate. Now I need to use my solubility rules to identify who's going to be the precipitate. Do I have a rule regarding potassium? Yes. Anything that contains a group 1A element is soluble. So I know that that is going to be in the aqueous phase. I have a rule that tells me anything that contains chloride is also soluble except silver, which is one of the exceptions to that solubility rules. Anytime you have a silver reacting with chloride, it's going to be a solid. It's not going to dissolve in water. So that would be the solid, which means that this would be my precipitate, or the solid that would come out of the solution. Finally, you need to balance, meaning you need to make sure that you have the same number of ions in each side. And in this equation we do. We've got one silver, one nitrate, one potassium, one chloride, one chloride. Let's look at another example where the balancing will become more of an issue. All right, let's take a look at this problem. You have barium nitrate reacting with sodium sulfate. First thing we want to do is list the ions. Remember, use the nomenclature rules, don't invent ions. Barium's in group 2A, so it would be a Ba2 plus ion. You've memorized that nitrate is NO3 negative. What about this 2 here? We don't care about that 2 here. We won't worry about that 2 until it comes to our balancing step. Right now we're listing the ions. The ion is nitrate, not NO3 sub 2, right? List the ions. Same thing over here, right? The ion is sodium. We've not memorized anything Na sub 2, right? Sodium's in group 1A, so we know that it's a +1 ion. We don't care about the 2 until it comes time for balancing. It's bonded to sulfate. Again, you've memorized that sulfate is 2 negative. For you at-home gamers, who didn't memorize the polyatomic ions, instead tried to just use a cheat sheet to get through it, this is the point in your career where you're going to begin to pay for that decision. If you don't know those polyatomic ions like the back of your hands, you're going to be in for a world of hurt for the rest of your life. So if you've avoided memorizing them, memorize them now. All right, so that's our so those are our ions. Now we're going to make new compounds by pairing the inside and the outside. Outside, inside. Barium's +2, sulfate is -2, so the compound they would form would be a 1-to-1 ratio. Same for our sodium nitrate. Sodium's +1, nitrate's -1, so it would be a 1-to-1 ratio. Remember, cations always go first, so that sodium needs to be moved to the front. So we'd have barium, sulfate, and we'd have sodium nitrate. Now we need to assign phases. Well, anything with a group 1A element is soluble. So we know right away that that's going to be aqueous. Well, anything that contains sulfate is supposed to be soluble, except, what's one of our exceptions to sulfate? Barium, right? We just had a whole example previously about that. Sulfate and barium are going to form a solid, so barium sulfate would be our precipitate here. Now, last but not least, we need to balance. I've got one barium here, so I'm good. I have 2 nitrates here. Now we have to pay attention to our 2. We have 2 nitrates over here. We only have 1 nitrate over here. So I need 2 of my sodium sulfates, 2 of my sodium nitrates. I've got 2 sodiums over here. I have 2 sodiums over here now, thanks to that 2 I just added. 1 sulfate here, 1 sulfate here. Just like balancing a normal chemical equation. Did I change my compound to reflect the fact I had 2 nitrates? No, I didn't, right? I just changed the number of my compound I have. Once you make your compounds in your second step, don't change their identity. To balance the chemical equation, only use those coefficients like you have been all along. All right, chemistry's easy, life is hard. Unless, of course, you're a fan of the bills. Then your suffering never ends. So why don't you write down the bills? B-I-L-L-S, bills. I have been so crazy rude. I have been hogging all the fun. And that's just rude of me. Here's some fun for you now. I am going to share the wealth. Why don't you try this one on your own? Pause me, try it on your own, and then check back for the solution here in a second. Hey, you guys actually paused me this time because these are just too much fun to resist. Kudos. Now, let's take a look. We're going to list our ions. We have calcium, that's in group 2A. We have hydroxide, right? We have potassium, group 1A. And phosphate, you've memorized, is 3 negative. We're going to make our new compounds. Outside, inside. Here our ratio is a little bit difficult. We've got calcium 2 plus, phosphate 3 negative. We crisscross applesauce to make our compounds. And we wind up with calcium 3, phosphate 2 to get those charges to cancel. +1 for the potassium, +1, -1 for the hydroxide. So it's a 1-to-1 ratio there. So we now have our 2 products. We've got calcium phosphate as 1 compound, and we have potassium hydroxide as the other compound. Now we use our solubility rules, and we know that anything that contains a group 1A element like potassium is always soluble. No exceptions. So that's going to be aqueous. Then we have potassium, we have our calcium phosphate. Do we have a rule regarding either calcium or phosphate? Yeah, we have a rule regarding phosphate. Anything that contains phosphate is insoluble. Is calcium an exception to the phosphate rule? No, calcium is not an exception to the phosphate rule. So it's going to form a solid, and it will wind up being our precipitate. And I know some of you have noticed a little pattern here where it seems like that our precipitate's always formed by our outside pairing. That's just a quirk of how I've written the problems. That's not a real rule. It's just happened that way, the way I've written it. It's not going to happen every time. Matter of fact, I'll give you some on the test where I designed it so that's not the case. So we have calcium phosphate as our precipitate or solid. We have potassium hydroxide aqueous. So now we need to balance. I have 1 calcium here. I have 3 over here. So I'm going to need to add a three in front of my calcium hydroxide. That gives me 3 calciums. But darn it, now it gives me 6 hydroxides, right? 2 times 3 is 6. So I'm going to need 6 hydroxides over here. When I do that, that gives me not just 6 hydroxides, but 6 potassiums as well. Over here, I only have 3 potassiums. What can I multiply 3 by to get 6? 2. So that gives me 6 potassiums now, but it also gives me 2 phosphates, which, hey, what do you know? That's exactly how many I need. So now I'm balanced and done. Boom! Dropping the mic. Chemistry's easy, life is hard.